Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on special functions and how to numerically evaluate them. In the past lectures, we looked at one of the very famous functions, which is called gamma function, and it's basically a generalization of the factorial. And I mentioned that we can very efficiently calculate or numerically evaluate the gamma function using this Weierstrass's definition by doing this summation first and then this multiplication and then evaluating the whole thing, right? And then there are other functions, there are other family of functions that are closely related to the gamma function, and one of them is called Digamma function, and it's related to the derivative of gamma function, and more specifically it's related to the derivative of the log of gamma function, log gamma. So log of gamma function is also called another function, log gamma. And the ddx of log of gamma is basically gamma prime over gamma. All right, and then we're not going to obviously we can use the definition of gamma function to calculate this, but then it requires at least three evaluations of the gamma function, one for the denominator and two for numerator, right? In order to numerically calculate gamma prime, we calculate gamma x plus h minus gamma x minus h over 2h. That's an approximation of derivative. But instead of doing that, we can use the series representation. And again, as we discussed in the previous lectures, power series are the most efficient ways of numerically evaluating a special function, a function that doesn't have that doesn't have a representation of finite functions, right? Special functions are always infinite number of terms. So what we do now, first of all, you see that because gamma of x is in the denominator for x equals gamma had singularities at 0, -1, -2, all the negative integers plus 0. So this function also has those singularities. And then when z or x is not equal to 0, -1, -2, and all the negative integers, then psi of x, this gamma function, is equal to minus gamma. This little gamma is the Euler-Mascheroni constant, and if you recall, the value is 0.577216, etc. It has more, this is like 6 decimal places of gamma. Minus gamma plus k from 0 to infinity, x minus 1 over k plus 1, k plus x. And this is very easy to evaluate, right? X minus 1 doesn't depend on k, so it comes out. And so we create a sum sequence, which basically is just a for loop that calculates the value of the series without the x minus 1, and at the end we add the x minus 1. So the sum sequence is just I from 0 to n minus 1, result plus equals 1 over I plus 1 or k plus 1 I plus x. All right, and then we use this this power series for a small x, and here less than or equal to 5, this series works fine. And then this little g here is this Euler-Mascheroni number, so minus g plus x minus 1 times sequence sum dot Richardson fourth order. We do a fourth order Richardson acceleration, and then evaluate at 100. So why do we do Richardson? Because look at this sum. When k is very large, the terms are approximately 1 over k squared, right? So if I sum from 0 to n term, and then the error becomes from n to infinity, and I can approximate it from integral from n to infinity of 1 over k squared dk, right? So the behavior of error is 1 over n, and that's a very, very slow convergence. All right, so we do a Richardson to make the error jump to 1 over n to the fourth power, and then we evaluate at 100. Maybe a second order Richardson is good enough, but we're doing a fourth order Richardson for good accuracy. Now if x is greater than 5, what we do, we use the large argument expansion, the series for large argument expansion, and it has a very good accuracy, and it gives us a fast evaluation and good accuracy for x greater than 5. And the series is psi of x is approximately log of x. This is the natural log, minus 1 over 2x minus 1 over 12x squared plus 1 over 120x4 minus 1 over 252x6 plus 1 over 240x8, etc. And you see that as x gets larger and larger, all these terms die off pretty quickly, and we end up with log of x minus 1 over 2x, right? So eventually the psi of x becomes asymptotic to log of x when x becomes very large. And the implementation is log of x minus 1 over 2x minus 1 over 12x squared plus 1 over 120x cubed minus 1 over 252x6 plus 1 over 240x8, etc. So these are all even powers, 1, 2, 4, 6, 8, 10, 12, 14, etc. All right? And then if x is negative, we are just using this power series, because this equality is exact, so we're just doing this for negative. Because remember, this only works for large argument, this only works for positive x, because log of x is only defined for positive x. And here's an example. I'm plotting both from Java and Python, and then you see we have very good accuracy for positive x for small and large values. And then as you can see, when x goes very large, we asymptotically approach a log function. And for negative x, you see that we have all these singularities, and these singularities come from the denominator here. So k goes from 0 to infinity. So if, for example, k is 0, then for x equals 0, we end up, the first term blows up. The second term has k equals 1. So if x is negative 1, the second term blows up. That's why we get all these blow-ups at negative integer numbers and 0. All right. So let's head to Eclipse and try to look at the code. I have this Digamma function. We have this Euler Mascheroni number. I have it to 3, 6, 9, 10 decimal places of accuracy. And for real value numbers x, Digamma, we have the power series for small arguments and for asymptotic for large. And if x is negative, I'm just using the power series with more terms, because eventually it has a very slow convergence, but it should get close to the actual value. And then so this is the Digamma. For complex, we do the same thing. So for complex, we have the same sequence, but it's complex, right? And then for a small argument, we have the same, and for large argument, we also have the same. So everything else is the same, except here x becomes a complex number, and in these functions, we also have complex numbers, all right? And I have written a test class, test Digamma, and in test 1, I'm just calculating the value at this x, which is minus 1.2. Let's put it to a positive number, 2.1 for example. So 2.1. So the value of Digamma function at 2.1 is this value. And if I fire up Mathematica, and let's try to look at the Mathematica. In Mathematica, Digamma, I believe it's Polygamma. And let's look at this. Polygamma, if I don't give it an integer parameter, it gives the Digamma function size. So 2.1, 485,336. We are getting 485,3359. So let's look at all the digits. 485,3359, 686. So we have 1, 2, 3, 4, 5, 6, 7, 8 decimal place of accuracy compared to Mathematica. All right. So in test 2, what I'm calculating is I'm actually looking at the sequence, the convergence of the sequence that we're using, this sequence, and see how fast it converges. So I'm not doing Richardson acceleration here, I'm just evaluating it. So let's run this. So we have to specify x, and x is 2.1. all right, so we already know the answer after the fourth order Richardson. So let's see how fast we get to this. Let me also run test 1 to see the actual value. All right, as you can see, up to 100, even 200, we have a very slow convergence, and eventually after 1000 terms, it's funny that we're getting only like 2 decimal places of accuracy. So it's unbelievable how slow this is, because again, if you look at the this power series, and it's an exact equality, so if you sum up infinite terms, you have to get the exact function, but it is painfully slow. So what we do, if we analyze, whenever we have a series and we want to accelerate it, we first analyze the behavior of the error. And for very large k, the terms are 1 over k squared, right? Whatever x is, doesn't matter. We get k squared, and the error becomes integral from n to infinity of dk over k squared. So the error becomes 1 over n. That's the very slow convergence, right? So what we're doing here, now we can accelerate it. So let's say Richardson fourth order and 1000 terms. Let's see what happens. Oh wow, look at this. See how fast this goes up. If we compare 200 terms, you see we are almost, after about like, I don't know, 10, maybe 20, we are almost there. So this is the power of acceleration. After 60, 80, 100 terms, we're almost there. And you see that we have this jiggling as expected. There's a bit of oscillation. That's why when we increase the order of acceleration, Richardson second order, third order, fourth order, we have to stick to smaller and smaller values, which makes sense because the acceleration is faster. But I want you to really appreciate how fast this is, right? After about 30 terms, we're at 0.45. Here we are almost there, right? We have I don't know how many decimal places of accuracy, 0.485336. We already have like 7 decimal places of accuracy, or 6 decimal places of accuracy. That's incredible. And remember what we're doing here. The reason that our implementation is very efficient and very accurate based on the power series is that when we do Richardson fourth order acceleration and then evaluate at 100, what we are actually doing, we are only calculating the sequence 4 times. So 4 evaluation of the sequence, which is very easy, right? If I go back, it's actually 5 times, right? Evaluate at n plus 1, n plus 2, n plus 3, and n plus 4. So we take 5 consecutive terms, which is extremely fast to calculate. But then we combine them in the clever way, the way that Richardson fourth order works, and it gives us an incredibly accurate approximation of the limit of the sequence, all right? That's how we accelerate the convergence. Now, what I would like to do here is for test 1 that calculates the digamma for a real number, let's give it a complex number. Let's see if we can change this to complex, and this is complaining here, so let's not do that, or maybe let's copy this first, and then I'm going here and we're going to change it to complex. So let's print our complex result and let's check with Mathematica. 2.1 plus j 64029, which is 6403 5485. All right, and of course I can look at the real part and imaginary part separately to see the accuracy. U.image, and let's look at the Mathematica. Real part, show all digits, 640, okay, 290, 37, so 36, we have 8 decimal places of accuracy. All right, which is very good, extremely good. And the next thing that I want to do is, I believe it's in test 3, to actually plot the function Digamma from 0.1 to 50. So I'm going to plot it, right? And as you can see, it eventually approaches a log. And in order to show you that, I can create another function log. Actually, there's a typo here. And then math.log of t. And then I want to plot this with color blue. And then the log here with color red. And as you can see, eventually, so the red one is the log, the blue one is Digamma. The blue one and the red one, they become asymptotic, all right? But for a small x values, Digamma has a sharper drop. And of course, I can export this to Python. So let's call this test, and then open it in a text file, select all of it, copy, go to our Jupyter notebook, paste it, right? And x0 and y0 are the Digamma, x1, y1 are the log function. So plt plot x0, y0, color B, and line style solid, and then label Java. And then what we want to do, we want to compare it with the scipy.special. So Python and line style dash red, and I will call the special scipy.special the Digamma and pass x0. And let me just run this one more time, and you see we have a very good match. All right, so this was the Digamma function. I hope you enjoyed this lecture, and I'll see you in the next one.